All right, so now we know how to graph them. So let's think about how the rates relate to each other. So let's start by thinking about the initial rates, but this will hold true the whole time. So at the very beginning, the rate of H2 here is just the change in H2 over the change in time. It could also be equal to the change in the concentration of H over the change in time. A lot of times we're going to use concentration instead of just moles, because that's just an easier way for us to look at things. So it's just how is it changing over time? That's your H2s. How is the H's changing over time? So the delta is always change, or final minus initial. Okay, so that's what the rate of H2 is equal to. And then the rate of N2 is just the change in N2 over the change in time, or the change in the concentration of N2 over the change in time. So brackets are concentration in molarity. Okay, so that's what that means. So here's the thing. These two are related to each other, and they're also related to the NH3. So the rate of NH3 is equal to the change in NH3 over the change in time, or the change in concentration of NH3 over the change in time. So here's the thing. These are each different numbers, but we can relate them all to each other because they're all related. This is going 3 times as fast as this is. So we can actually come up with a statement that says how they're all related. And we usually relate them to the rate of reaction. The rate of reaction is how fast each turn of the reaction goes per unit of time. Okay, so usually it'll be the same, basically the same, as whatever's a 1 in the reaction. If you have any coefficients of 1, that's kind of going about the same speed of the rate of reaction. So let's move everything. So how is the rate of reaction equal to the rate of all these things? Okay. So the rate of reaction is equal to the change in H2 over time. Except when H2 changes over time, H2 is going down, making it negative. And the rate of reaction is always positive. So we're going to multiply this by -1 to make that negative rate into a positive rate. Okay, the other thing that we need to do is take into account this 3 here. This H2 is 3 times as fast. So the rate of H2 is 3 times the speed of reaction. Basically, H2's rate is equal to 3 times the rate of reaction. So to get this to equal rate of reaction, we're going to divide both sides by 3, so we end up with a 3 down here. So really the rate of reaction is equal to -1/3 times the rate of H. Now remember, the rate of H is this segment right here. So whatever number the rate of H is there, and we times it by -1/3, that equals the rate of reaction. So this is also equal to the same thing for N2. But N2 is a reactant, so it's going down, so we want to make that positive. But there's no coefficient, so this is the same. And these numbers should all equal the change in NH3 over time. And this one gets a 2 on the bottom, because this is going 2 times as fast as the reaction, so we divide it by 2 to make it equal the reaction. So let's look at some numbers here. So let's erase some things. So if my rate of H2 is going down at a rate of, say, 6 molarity per second. So molarity per second is a very common unit for this. So it's how much molarities we're losing a second. So it's going down that fast, which means it's negative rate. So it's going down 6 molarity per second. So if we calculate final minus initial, we'll get a negative number. If that's the case, we can plug in here and find a rate of reaction. So our rate of reaction, sometimes you write it like this with RxN. It's going to be equal to -1/3 times that -6 molarity per second, which is going to equal 2 molarity per second. We can also from that find the rate of all the other components. So I can use these two and equal them to each other. So negative 1/3 times that negative 6 molarity per second equals negative the rate of N2. So this means if we do this math, this is 2 again, right? So 2 is equal to negative N2 over delta T. So really N2, this negative goes over here, is also negative 2, which we said N2 is about the same as the rate of reaction, but negative because it's going down because it's a reactant. So that makes sense. Reactants go down, so they have negative rates. So let's also do the last one. From this data, can we figure out the NH3 rate? And remember, when we're solving for a rate, we're solving for what we said over here was its actual formula. So this piece, without the 2, that's what we're looking for. That's the rate of NH3. So then we can put these two together. Negative 1/3 times that rate is equal to 1/2 times the rate of NH3. So what I'll get is 2 equals 1/2 NH3 delta T multiplied by 2, so 4 is the rate of NH3. And if you'll notice, these ratios do match our coefficients here because it goes 3, 1, 2, and these stay relative to each other. So the rates stay relative, just like the coefficients. So this is like if we had doubled everything. Everything doubles. So that's how we use this. So let's see one more example. Come on, one more example. Okay, so let's do this other part over here. So now we have another one. So this time I'm just going to start at the beginning. The rate of the overall reaction is equal to what? So it's going to be equal to the rate of Fe, which is delta Fe over delta T, but we're going to times this by 1/4 because Fe is going 4 times too fast compared to the reaction. This is going to be equal to, oh, and also it's negative, right, because this is going down. Reactants go down and products go up. So these need negatives to make sure that everything stays positive. So now oxygen's going to get a negative 1/3 in front of its rate. And Fe2O3 is going to get a positive 1/2, not its rate. And I can pick any 2 pieces of this. They're all equal to each other, so I can use any of them to solve for anything else. And if they're telling me the rate of something, they're telling me just this piece. So I'd plug that number in and then solve for whatever else I'm looking for. So we'll see some examples of how to use these numbers later, but for now we're trying to be able to write this expression. How does the rate of each thing compare to the rate of reaction? So we're looking to be able to add these numbers. So the things we need to remember, all reactants get a negative. Now sometimes you got to be careful. Sometimes it says the rate of decrease is a number and they give you a positive number. The key thing is that all rates should, the reaction rates should always be positive. So all reaction rates are positive because they're going forward. Kind of like if you're driving a car, and if you drive it backwards, it's still positive. So we want it to be positive. And the other thing we need to remember is that we divide the rate of a reactant or product by its coefficient. Sorry about my writing. To make the rate of reaction. Those are the 2 main things we're doing here. So all you got to do next is practice.